Hey, everybody. We're going to be talking about Chapter 9, Estimation and Confidence Intervals. So I'm sure many of you have heard of confidence intervals before. Oftentimes they're accompanied, by the 95% confidence interval, 99% confidence interval. So we're going to talk about what that means and how we should think about them. So here's some learning objectives. I'm going to skip them. But the first thing we need to talk about is a point estimate. A point estimate is a statistic that you computed from sample information that's supposed to estimate a population parameter. So everything we've been doing, we collect a sample of data, we estimate that sample's average. That's our point estimate. So we know that here's our point estimate, right? Great. We also know that this is going to approximate the population parameter, but there's some sample error, right? Because we're not going to get it perfectly. So if we collect a second sample and we calculate that information or that point estimate, that average, that whatever we're looking at, that's also going to be different. So a lot of times there's only one sample that you can collect, right? Suppose, there are 1 million home sales in America, but you're only able to observe a few of them because of data restrictions, or maybe you're only allowed to look at the ones in this specific state or in this county, whatever. Well, sometimes there's only one sample you can collect. Or, if you're the ACS, the American Community Survey, you're only sampling 1%. You can't do 1% 10 times. You only get to do it once. So you calculate this point estimate, but you have to recognize that there's going to be variability in that. And you want to figure out a way, how can you make some interval where you kind of say, okay, here's my point estimate, but the true value is between here and here, right? These two numbers on either side of the point estimate, one a little bit lower, one a little bit higher, and say, here's my, here's the confidence interval. Here's the interval of values that it possibly could be. So this is what a confidence interval is. It's a range of values within the population parameter is expected to occur. So I calculate some sample average, and I'm going to make plus or minus a little bit on either side. So I can say, okay, this is going to be, the range. And within this range, I think the true population parameter is going to be located within here. So there's a few different factors that determine your confidence interval. First is going to be the number of observations in your sample. So this is going to be n. This is going to be because of pretty much what we talked about before, where we had the larger your sample size, the more precise you're going to be, right? So this is going to determine how wide your confidence interval is. If your n is very, very large, your interval is going to be very small. This is because more precision means a smaller interval. The next one is going to be the variability in the population. So of course, if the population has huge swings all over the place, then this is going to have to be reflected in the confidence interval. So this is just usually used by the sample standard deviation S. And then finally, we want the desired level of confidence. This is a bit tricky, but the way to think about this is oftentimes people ask for the 90% confidence interval, the 95% confidence interval, and the 99% confidence interval. So we're going to have to scale the confidence interval by how confident we want to be. So n is going to reduce our confidence interval, make it smaller. An increase in the variability of the standard deviation in the original population is going to increase our confidence interval. So n is going to reduce it. Larger n's will make it smaller. Larger variance is going to make it larger. And desired confidence, if we want to be more confident that the population parameter falls within, we have to make it larger and larger. So as an example, if we want to be 100% confident that the population parameter is within our confidence interval, we should make that confidence interval as large as we possibly can. It should be from negative infinity to positive infinity. That gives me a 100% chance that it is within the confidence interval. On the other hand, if I want to be, not confident at all, right? 0% confidence, I want to just pick the parameter itself, right? I want to pick the point estimate. That's going to be 0% confident. So as confidence is increasing, so is the interval size. So here's how we would create a confidence interval if we know the population standard deviation. This is a little bit of a heroic assumption, but we'll talk about what happens if we don't know this in a little bit. So let's suppose you know the population standard deviation. Great. We're going to have our X bar, which is going to be our point estimate, and then plus or minus a little bit, right? That little bit is going to be Z times sigma divided by square root of n. So sigma divided by square root of n is our standard error. So it's the standard deviation of the population divided by the square root of n. The square root of n is just going to be, again, as n increases, this whole value here is going to reduce because its denominator is going to get larger. If this gets larger, the variance gets larger. This whole thing is also going to get larger. And then Z is going to be the Z value for a particular confidence level. So if I want, like, say, the 95% confidence interval, I want to divide 95 by 2 because I want to split the 95 over both of that normal distribution. And I want to calculate what number gives me that value. So we're going to see this on the next slide. So again, let's say we want a 95% confidence interval. We're going to divide the confidence interval by half. So 95 is going to be split over both sides, as you can see here. So we're going to get 0.475 on either side. And we're going to find where the Z value that gives us 0.475. When we do this, we're going to get 1.96. So now our Z value is going to be 1.96 times the standard error. So that's going to be plus that value and minus that value off of our point estimate. So in this example, we say, or I'll kind of leave this leave this one up to you. But essentially, the thing to note is here's the standard deviation, 2.050 divided by square root of n, which is 49, and then 1.96 for a 95% confidence interval. Now, what if we don't know sigma? We have to use a little bit different of a formula. The formula is only going to change insofar that instead of sigma, we now have S. And if you remember, S is just the sample standard deviation. So we already know how to calculate this. And then on a question on an exam, I'll give this to you. And we have T. Now, we have not seen T before, but T is just a new distribution that's very, very similar to the normal distribution, but it's going to depend on another thing. It's going to depend on our quote unquote degrees of freedom. And I'll talk about that in one moment. But essentially, once you find your T value, which is going to be effectively your quantification of level of confidence, you have your standard deviation and you have your N, you can create your confidence interval the exact same way. So you have your X plus a little bit, minus a little bit, and you're saying between these two numbers, the true population parameter is going to fall. So here are some characteristics of the T distribution. First, it's a continuous distribution. It's mound-shaped and symmetrical. So same thing as the normal distribution, but it's flatter, meaning that there's more uncertainty, right? That would be indicative of a slightly larger standard deviation. And then there's a family of T distributions. It depends on the number of degrees of freedom. So degrees of freedom is directly tied to your sample size, at least in this case. So here we're going to use degrees of freedom is always going to be equal n minus 1. So we're going to pick for a confidence interval, we're going to pick what level of confidence we want, in this case 95%. And we're going to go down and see what our degrees of freedom are. If we have 10 observations, we will use a degrees of freedom of 2.262. Now, as our n approaches infinity, as it gets larger and larger and larger, the t distribution is going to converge to the z distribution. So they're very, very, very similar. It's just that the t distribution is a little bit better with uncertainty because we don't know the true population standard deviation. That's the only difference. So here's an example. I'll let you go through it. And now we can also calculate confidence intervals for proportions. So in this case, we can think about what percent of people in the class have a pet cat, right? I have a pet cat, maybe other people have pet cats, and we can look at the total number of people who have cats divided by the total number of people. And this would be a sample proportion, right? This is not indicative of all of West Virginia University. This is not indicative of the population at whole, but it's a good estimate, right? Maybe it's a good estimate. Maybe there's selection bias in there, but regardless, you're able to calculate the sample proportion. And then from here, we can also just calculate our confidence interval for this proportion as well. So this formula is going to be, again, relatively similar. We have our z value. We have our square root of n. Notice how the square root is over the entire thing here. And we have p times 1 minus b. This is the variance of a proportion. So when we put the square root over both, we're technically getting the standard deviation of the proportion divided by the square root of n. So this is really just exactly the same. There's really no difference other than the way you calculate it. We're still calculating our proportion, or rather our confidence interval, the same exact way. It's z times standard deviation divided by square root of n. And you'll notice for this one, we're using z again. For all proportions here, we're going to use z. Now there's two more things I want to talk about. This first one is going to be talking about how do we determine our sample size. So oftentimes when, suppose you want to do a survey, or you're the American Community Survey and you want to figure out, okay, well, how many people do I need to really survey? Well, there's going to be a few factors that you want to consider. The first one is the margin of error. So that plus or minus, how far off do you want to be? If you're calculating the percent of people who want cats, you might have to do something like, you want to be within 1%. That would be your margin of error, 1%. Maybe if you're talking about average salary, maybe you want to say, I want to be within $5,000, right? So whatever your margin of error is going to be. Next is your desired level of confidence. So your Z value for whatever. And then finally, the variation in the population. If you have any estimate of the variation, from here, you'll be able to calculate the sample size that you need to collect in order to achieve the margin of error that you're interested in. Again, just this final disclaimer here, the result is not always a whole number. And you might have a fraction, you might have like 512.6. You should probably just round up to 550 or some number, 520, something like this. Any number that's a little bit above whatever you end up calculating, just for safety. So here's an example that you can kind of go through by yourself. Here's how you would determine a sample size for proportion. It's very, very similar. If you kind of remember the math I was saying right before, P times 1 minus P is the variance. So we can kind of remove the standard deviation out of this squared fraction. It's the same exact formula. Here's an example. And the last thing I want to talk about is the finite population adjustment. A lot of times we, in applied empirical research, we don't really consider this, though it is something to think about. So the finite population adjustment says, okay, if your sample size is 49, right? The square root of n is 7, and you can apply that right directly to your estimate. However, if you're talking about sampling states in the US, and you're thinking about how should I think about doing 49 states out of 50. You have almost you pretty much have a population. You just are missing one state. Maybe Hawaii doesn't have data. Maybe Arkansas doesn't have data. Something like this. Or maybe they wouldn't release data to you, right? So you can adjust your confidence interval by this finite population correction factor to kind of account for the fact that, hey, yeah, I only have 49 observations, which is a decent amount, but it's 49 out of 50. It's quite a lot. So for example, in this case, this correction factor right here would be 50 minus 49, so the square root of 1 divided by 49. So the square root of 1 over 49 is a very, very, very small number. And what we're going to do is we're going to multiply it. So you can see here, we have our mean value here. Maybe I'll use the formula. You have mean value here, plus or minus t times the square root, or times standard deviation divided by the square root of n. And then we're just multiplying by this right here. Now, if we're talking about 1 over the square root of 1 over 49, that's going to be almost 0, right? That confidence interval is going to be so small because you have almost all the information. In fact, if you had 50, right, it would be the square root of 0 over the square root of 49. Now, if you've sampled all 50, you don't actually need an interval because you have the actual data. You no longer need an interval to say that the population parameter is between these two values. You just have the population parameter. So this is just something to keep in mind when you are working with finite populations. Oftentimes we assume an infinite population, and what we're observing is just a sample. But this is a good example to kind of go through and show how if there's a finite population, there's an adjustment to be made that will reduce your confidence interval.